Hi guys, this is my video for TED Talk presentation in the college. I have a TED Talk presentation on apprenticeship subject. So I have selected this topic as my TED Talk video presentation. Abstract. Multispectral imaging enables discrimination of spectra beyond the 3D spectral space of human vision. Most multispectral systems are complex and bulky. In simpler monolithic designs usually require several pixels in order to generate one multispectral data point. Here we use a vertical overflow train structure to enable monolithic multispectral imaging in a single pixel. We show that by controlling the subtract bias voltage, it is possible to change the effective depth of the photodiode, thus enabling dynamic tuning of the pixel spectral response. This is from the first slide. Go to the next slide. Introduction. Over the past few decades, multispectral imaging has been identified as an invaluable tool for many applications, including military surveillance, medical and biological diagnosis, and agriculture. These techniques usually require a diffractive optical element such as a prism or a metal grating in order to spatially spread the spectrum over many pixels. An array of spectral filters can be implemented on the top of the image to achieve a similar purpose. Using a filter array is also the most common technique for RGB color reproduction in modern image sensors, where each filter transmits only a certain color, making the pixel it is mounted on sensitive to a certain fragment of the picture. This is from this side. Next slide. Four sensors present a different approach for color imaging by utilizing the wavelength dependent light absorption length in silicon. A 4-on pixel comprises of a vertical stack of the three PN junctions, each collection photoelectrons from a different depth, that is from a different spectral range. Therefore, no signal is lost due to filtering, and each photosite can generate the clear color information without interpolation and consequently loss of effective resolution. Another device which is similar separation principle is the transfer field director in a TFT pixel. Photo-generated charge carriers from different depths are swept to different collection sites by electric field generated by surfaces. This device structure also to dynamically tune the pixel spectrum response by controlling the electrode voltages and therefore the electric field in the pixel. This capability, however, comes at the cost of a relatively complex pixel design that is not compatible with modern thin photodiode architecture. The Wood structure, the Viewed structure mechanism. The Wood structure was originally used as a blooming suppression machine mechanism in the interline transfer CCDS. In these devices, the photodiode is formed in a lightly doped PVL in an N-type substrate. When the PVL is depleted, the N photodiode, PVL and PN substrate act respectively as the emitter base and collector of a vertical PDT impulse through mode. When the photodiode saturates its charge carriers cross the depletion region and are drained to the substrate. The electrons cannot diffuse freely to adjacent photodiodes and the blooming phenomenon is prevented. When the structure is combined with the LPD, it is possible to use it as a global electronic setup. Increasing the substrate bias voltage to a certain value eliminates the potential barrier between the photodiode and the substrate and all the electrons are stored in the photodiode or drained. Using this mechanism, the photodiode can be drained just before the result exposure period starts. The exposure period ends, ends by transferring the photoelectrons from the photodiode as a storage area. Figure 1. One-dimensional illustration of potential levels beneath the center of the single photodiode in a pixel with broad structure mechanism. Endopole regions are marked in orange and the pedopole regions are marked in blue. It is shown that photoelectrons will be either gathered to the photodiode or drained to the substrate, depending on where they are generated related to the potential barrier. As the substrate bias potential is raised, the potential barrier becomes shallower and long wavelength signal is more likely to be drained. For certain voltage, the PL becomes completely depleted and punch through current starts flowing from the photodiode to the substrate. For high pass voltages, the barrier is removed completely. This state is usually referred to as a closed state of the electronic shutter. Spectral response control using the Watt barrier. A complete analytical treatment of a junction transistor in punch through mode was derived by J. Loshkosh et al. 19. Here we will apply this derivation to a photodiode with a VOD barrier in order to develop understanding of how the barrier with therefore the pixel spectral response are controlled by the substrate bias voltage. The expression for the potential barrier formed in a depletion typically sandwich structure between two more highly endopole agencies. P of x equals to A over into 2x J over by x 2x direction. In this expression above WP is the P1 with V is the change in substrate voltage bias and VJO and XO are the barrier right and crystal location for V equals to respectively. The crystal location depends on the substrate voltage, which we will define as the effective photodiode depth developed is developed, which is equation 2. Equation 2. We go to the next slide. It becomes about that by applying higher bias to the substrate, it is possible to reduce the photodiode's maximum correction depth defined by assuming that only electron elected into the barrier are collected, and by using the Lambert law, we get the following expression for the photocurrent depends on the effective diode depth and on the absorption coefficient. It is now possible to obtain a theoretical spectral response for simple photodiode design. For example, figure 2b shows the spectral response for a device with WPP 5 million and XJO is version. This is some PCAD simulations of P2D pixel with VOD barrier. The analytical model in the previous section demonstrated the principle of controlling the pixel spectral response via substrate voltage bias, and this model, however, does not take into account several factors that exist in practical areas such as non-uniform doping of the even or the complex structure of the pixel. These are expected to introduce variation from the theoretical results. In order to study the spectral response modulation in a more realistic conditions, we use the process and device TCAD simulations even through the VOD mechanism is primarily used in CCDS. We usually use 0.18 million ampere CMOS image sensor process flow through the photodiode simulation is this. Experiment results. In order to perform an experiment study of the probability to control the spectral response as explained, user of the shelf CCDS with no color filter area and a watershed mechanism. The substrate pin of the CCD was connected to an external voltage supply to enable biasing of the substrate to any arbitrary value. The selector sensor was placed in front of a monochromator and the average pixel response for different wavelengths versus different substrate voltage was measured. The results normalized for the maximal response for each wavelength are presented. It is apparent from the figure that as the substrate voltage is reduced, the pixel aperture for the wavelength becomes noticeably different. This response is revealed the fine details of the VOD mechanical operation can be divided into four stages. These are the four stages. We yield 0 minus 1 of it. There is no change in the pixel response since the P-well is not completely depleted in the potential barrier takes some mode. The next second one, the P-well is depleted and the potential barrier becomes shallower as the bias voltage increases. As a result, the response to longer wavelengths is reduced. Third one, the well capacity of the photodiode itself can sharply reduce due to the reflection and the potential barrier lowering. Strong points through the current and the integrated photoelectrons. Fourth, the VOD barrier is completely reduced and all the free electrons are drained. It is impossible to roughly calculate the theoretical limit for the spectral resolution and intensity for what the using the measurements of the substrate bias of 1 volt and the one with the substrate bias of 5 volt. Where is the raw response vector. A set of color collaboration patches with unknown RGB values leads the Vector of the calibration RGB values. RGB is known as the patches in measuring different voltage biases. RF or ARF. Using the two calibration vectors, the transformation of matrix is construction by obtaining the least square solution of the underestimated linear system with the calibration vector. Conclusion. The mechanism to dynamically control the pixel vector's response using the V-body structure was presented. This mechanism has many potential advantages over other methods of statistical imaging. It generates all the spectral data in a single pixel, does not use obstructive filters, and can be controlled dynamically by changing the substrate bias voltage. Since the wavelength separation is based on voltage and absorption depth, it has a continuous nature and is not limited by predefined filters, as we should show it here traits to make the VOD mechanism a natural candidate for an elegant and practical multispectral imager from the pixel design in point of view. The mechanism is compatible with filled photodiode pixel type. It can be implemented in existing pixels without major design change. Moreover, it is an industry proven mechanism already implemented in many. Thank you.